This is part 2 of number 2 with the suspended sign. I apologize for getting stopped. I had to stop it and pick it back up again. But these are my two y parts, and both of those are up. F2y, F1y. And then I have my x portion as well, F2x, F1x. So I've just labeled everything. What's nice is I usually can get away with just doing x stuff, and I also don't need the mass because it's not accelerating anyway, so the right half of the equation ends up being 0. Over here I can come up with a numerical answer, f1 times the cosine of theta, which is 183 times the cosine of 43. So f1x is 133.8. And over here, I can't find the number yet because I need f2. That's just plain old f2, the hypotenuse, times the cosine of 55. So those are my two equations that I'm going to end up using. I could also find f1y, f2y. I would be unknown, and I know the weight. But I don't even need them for these, for this particular kind of static equilibrium problem. So I'm going to sum the forces in the x and sum them in the y as well. And in the x is going to be easier because I only have 2. So if I start just like before, I start like this, and I only have 2 here. I have f2x that's forward and minus f1x that's backwards equals m times 0. And again, this is specific to this problem, that ax equals 0 because it's not accelerating, because it's an equilibrium. So I've got f2x minus 133.8 equals 0, or f2x has to equal 133.8. And this is half of my answer. This is, well, I'm halfway there. So this is just the x portion. But remember, I'm trying to find f2. So if I know f2x equals that, and f2x equals f2 times cosine of 55, I can set these two equations equal to each other. And I end up with f2 times the cosine of 55 equals 133.8. And divide by the cosine of 55 to solve. And f2 is equal to 233. That's your final answer. You can also find all of this information by doing the sum of the forces in the y. You're just going to have these two up and that one down, but you can still, you'll get the same answer regardless.